Hi, I'm Deepthakaran Rangarajan. Welcome to my presentation on the real-time stream processing using Kafka and Storm. This is my final project in Big Data Analytics course that I'm doing in Harvard Extension School. Let's go to the presentation. Before Hadoop, we didn't have any good framework to process large files. Imagine you having a file with terabytes of data. Without having a high-end machine, you would probably break that big file into smaller chunks and run your programs on those smaller chunks and aggregate the data. But it's not very convenient. So now after Hadoop introduced this MapReduce framework, you can submit your file and Hadoop would divide that file into smaller chunks and move it across different nodes and run your MapReduce programs on those different nodes and collect the results for you. It's all good, but Hadoop is basically batch processing. That means it expects an input file to be there when it starts processing. So you cannot change your data when Hadoop is doing its job. But people want results faster. So for example, if you're recommending a product based on what the user is clicking on your website, then collecting the logs and running your MapReduce program and then getting the results back into the web page, it takes some time. So I think there are still websites that do that. You collect logs and run MapReduce programs and get the results back in production, but it's not an elegant solution. It would be great if there is a framework that supports your real-time data processing. And there are a lot of frameworks that support real-time data processing, but what about big data as well as really fast data? So there are many frameworks after Hadoop that supports real-time processing, and Storm is one of those frameworks which is doing a good job, and a lot of companies have adopted Storm along with other frameworks. Um, so let's look at Storm. What is Storm? A distributed real-time computation system for processing fast, large streams of data. It was originally created by Nathan Mars and a team at Backtype, and Backtype was acquired by Twitter. Then the whole project was open source in 2011. It was initially written in Clojure and then written in Java as well. It's really fast. So you can see it can process 1 million 100-byte messages per second per node. And even though they say that Storm easily integrates with any queuing system and any database system, if your database system or queuing system is not supported by Storm out of box, you have to write some code to integrate your messages into Storm. What are the features of Apache Storm? Allocation of work across nodes. The framework takes care of this, so you don't have to do the job of packing your programs and running them in different nodes. And it guarantees message processing. Each message is guaranteed to be processed at least once. So there is configurable amount of time within which a message should get processed, else the Storm would ask the data provider to replay the message. And it's fault tolerant. If a node goes down or if a task goes down, then Storm would start another task based on the availability of nodes. So it's horizontally scalable and it's very efficient and it's very simple to program. At the end of the presentation, I'll give you I'll present a slide where you can see what are things you need to do to get your Storm program up and running. So what are the components of Apache Storm? There is this Nimbus node, which is the master node, which is also a single point of failure. That's one of the drawbacks of Storm. It's similar to Hadoop's job tracker, as you can pretty much read from the slide, that it distributes your code, it launches workers across the cluster, and it monitors computation and relocates tasks if needed. And Zookeeper is a different service it's an individual project. It's not part of Storm itself, but Storm makes use of Zookeeper to track the other nodes. The computation nodes heartbeat with Zookeeper so that Nimbus can keep track of those things. Your supervisors are daemons running on the computation nodes that the Nimbus makes use of to start and stop workers in that node. So what are some of the jargons in Storm? You have a spout, which is basically a data provider, and a bolt, which is a processing unit, and a topology. Topology is basically how you arrange your spouts and bolts. So in the example below, you can see there is a word reader spout, which is the data provider, which reads from a text file, and it gives the output to word normalizer, which would, I assume, is breaking the sentences into words, and giving its output to word counter bolt, which is probably aggregating the results. So grouping defines how a message is transferred between one component of a storm to another component of a storm. So there are different types of grouping. Shuffle grouping, meaning that you tell the framework to do random grouping. It means an output from any component can go to any other component in the storm. Fields grouping, this comes handy when you're doing a word count program where you want the same word going to same bolt so you don't need to do additional processing to aggregate the results. All grouping, meaning that every output goes to every other bolt in the topology. You can define a custom grouping if you want. Direct grouping, meaning you can say, hey, I want this component to process my message, so you can use the component ID to do this. Global grouping, meaning you're sending all the output of all the bolts in one level to one bolt instance. So you can think of this bolt instance as a sink where it collects all the data and aggregates the results. So I said it's really simple. How simple is it? Your spout would implement an iRich spout where the important method is the next tuple. This gets called by the framework, and then you need to give data back to the framework. And your bolt would implement iRich bolt interface. There are other methods in the interface as well, but the important one is execute, which takes a tuple, which is the output of your spout, or it can also come from another bolt, and it processes the data here and then emits it back to the framework, and then the framework decides to send it to another bolt or not based on the configuration. And you say collector.ag, meaning that you have successfully processed this message, and then the framework can make use of this and track the data. So let's create a topology and run. So use topology builder to create your topology. You say builder.setSpout, you give a unique name, and then you give the instance for that. And you say builder.setBolt, and you give a unique name and the instance, and you say I want shuffle grouping, and shuffle grouping from your input. Your input is the word reader, which is the spout that you defined previously. So the next bolt is the word counter bolt, which takes its input from the previous bolt, which is word normalizer. And Storm operates in two different modes, local mode and remote mode. Local mode is helpful for debugging, and once your program is ready to go, you can use the remote mode. The class is Storm Submitter. You can use it to run it in production. That's it. Now we know what Storm is capable of. To test Storm's peak efficiency, we need a really high throughput framework to give input to Storm. That's where Kafka comes in. Kafka is a publish subscribe messaging rethought as a distributed commit log. Kafka derives a lot of its implementation from a commit log implementation that you would see in a database. It aims to provide a high throughput, low latency platform for handling real-time feed. It was originally developed in LinkedIn to track user activities on their web pages. It was open source in 2011 to Apache. It was written in Scala, and now people are developing in Java. It's fast. A single Kafka broker can handle hundreds of megabytes of reads and writes per second from thousands of clients. It depends on how you use Kafka. In Kafka 0.7, there was no acknowledgement between a producer and a broker. So pretty much the reads and writes are happening very quickly. But in Kafka 0.8, you have a way to ask the broker to acknowledge your messages. And if you use this model, then writes are going to take some time, and reads are pretty much the same. What are the features of Apache Kafka? Durability, this is the one it derived from the commit log implementation, where messages are persisted on disk and replicated within the cluster to prevent data loss. It's highly scalable. If you have a lot of messages coming in, you can add a new broker to your Kafka cluster, and as long as your publisher knows which partition it should send to, then your messages are handled good. It's fault tolerant. If one of the brokers go down, the brokers decide among themselves using the zookeeper, and they would re-elect a new leader for the partitions that the node was acting as a leader. Kafka is really efficient. They have a smart approach when writing data to disk. Instead of opting for JVM to manage the data in memory, they've opted for disks to do the job, and they claim that disks are much faster when dealing with large amounts of data. Let's look at the terminologies in Kafka. We have topics, partitions, brokers, data producers, and data consumers. Topics are a way to group messages, and partitions are a way you divide messages for that topic, and brokers are where you store your messages. If you can see in the example, we're producing messages for the topic Zerg Hydra, and the messages are stored in broker 1, broker 2, and broker 3. You can see the replications as well. And this topic has 3 partitions: partition 0, partition 1, partition 2. And each broker acts as a leader for the partitions. For example, broker 1 is the leader for partition 0, and similarly broker 2 and broker 3. So a consumer, to get a message from partition 0, it would get from broker 1, even though it's replicated in broker 2 and broker 3. Let's look at producers. Producers need to know one broker at least to query for partitions. Producers send messages with topics and a key. A key is optional. A key is used to decide which partition to publish the message to. A custom partitioner helps to have more control. Default partitioner uses mod computation on your key to identify partitions. If your key is null, message is assigned to a random partition. Let's look at consumers. There are 2 consumer APIs provided by Kafka to pull data out of brokers. So there's a high-level consumer, which is useful if you don't care about the old messages. But if you need to process new messages using old messages, then you would use a simple consumer that gives you more control over the messages that you get from the brokers. Let's look at the diagram here. Messages are consumed from brokers through consumer groups. A consumer group would register for a topic, and the server would give you the messages that are under that topic. So, for example, if you have more consumers in a consumer group than a partition, you wouldn't receive any message for that extra consumer. But if you have equal number, then and each partition is assigned to each consumer in a consumer group. But if you have lesser number of consumers in a consumer group than the available partitions, then each consumer would get more message from the partitions. And that's it. These are my references. Please follow my next video to see how Kafka and Storm is integrated to solve a problem. Thank you.